Hello, in our practical today, we'll be covering content from worksheet 4. It might say worksheet 5 on here, but just know that this is worksheet 4. You're in the right place. The first half of today should be revision, as we'll be talking about independent samples t-test. And the second half, we'll start getting into one-way ANOVA. Now, the purpose of the practical today is to expand our knowledge of statistical analyses. So you'll see that one-way ANOVA really is an extension of t-test. It's a more sophisticated version of the t-test, and it's specifically for when we have more than two levels of our independent variable. So we'll talk about that, what that means in just a second. And in this worksheet, you were asked to refer to two separate data sets. Each data set is exactly the same, it's just in a slightly different format. One format is better suited for the t-test, and the other format is necessary for a one-way ANOVA. Before we can even run these analyses in Stata, we have to have a better understanding of what our variables are and what our research questions are asking. And according to this background information, the researchers were interested to see if eating soy meals influenced sexual reproductive health. More specifically, we're interested in whether eating no soy meals per week, one soy meal per week, four soy meals, or seven soy meals per week for an entire year will influence sperm count in adult males. And in the first data set we're working with, we have four separate variables. One variable contains the sperm count for men who ate no soy meals per week. Next is the sperm count for men who ate one soy meal per week, four soy meals per week, and finally seven soy meals per week. Now, while these are presented as four separate variables, there are actually four levels of the same exact independent variable. And our independent variable is simply how many soy meals men ate per week. And as researchers, we want to know if that influences sperm count. Now, if you recall with regression, we were interested in predicting our dependent variable based on the behavior of our independent variable. With t-test and ANOVA, however, we're interested in if there is a significant difference, if there is a mean difference in our dependent variable as a function of our independent variable or variables. So while regression and ANOVA are mathematically linked, we're really asking two different things here. So make sure to keep that in mind when identifying research questions and hypotheses. And now there are some keywords to look for when identifying the research questions. For example, our first research question in the first half of the practical asks if males who did not eat any soy have significantly higher sperm count from those who ate one soy meal per week. Now that keyword is really important because not only does it tell us that we're looking for a significant difference, but it's also telling us the direction that we expect that difference to be. This will become very important when we examine the results of the t-test. We have two more research questions for the first half of the practical. The second research question asks if there's a significant difference for those who did not eat soy compared to those who ate four soy meals per week. Okay, and in this case, we're just asking, is the sperm count here significantly different? We're not anticipating any sort of direction. And same thing with our third research question. Do males who did not eat soy have significantly different sperm count from those who ate seven soy meals per week? So let's keep that in mind as we move over to Stata to test these research questions. Now, of course, the first thing we have to do is import our data set. We're using the same series of commands we've been using the past few weeks. Right, and we can see that we have four variables listed here. No soy, one soy, four soy, and seven soy. Okay, and let's take a quick look at these data in the editor window. Now remember that in each of these variables, the values refer to the actual sperm count. So we have the four levels of our independent variables and the overall sperm count for each level. Remember, with our t-test, we want to compare the difference in mean sperm count as a function of number of soy meals eaten. Now, we're going to move right into the t-test from here. I'm going to save assumptions testing for the one-way ANOVA. Because this is revision, we're going to go through this a little quickly. Now, remember, our first research question asks if males who did not eat soy have significantly higher sperm count from those who ate one soy meal per week. The command here is simply t-test, no soy equals 1 soy. So we're kind of writing out the null hypothesis here already. And finally, it's important to include the subcommand unpaired. Now, let's think about what that actually means. This means that we're going to be running an independent samples t-test. So if you ever see unpaired, that's the same thing as an independent samples. That simply means that the group who had no soy meals are different from the group who had 1 soy meals. All right, so we didn't measure one group of men who had no soy meals, then had them eat 1 soy meals and measured them again. So these are completely separate groups of people. And this is important to identify because the calculation of the overall t statistic is going to be slightly different for an unpaired or a paired samples t-test. So when you're working with groups that are independent of each other, make sure to include this unpaired here. All right, so let's run the command and work through the output. Right, now we get a lot of really good information from the t-test output. In fact, a lot of this overlaps with some of the summary statistics we'd be interested in anyways. Right? And you can see that we have one row for participants who had no soy meals and one row for participants who had 1 soy meal per week. Right? We could see that we have equal number of observations in each group. And then we also have the mean for no soy and 1 soy. And we also have the standard error and the standard deviation. Right, and then finally, we have our 95% confidence intervals. And when interpreting the 95% confidence interval, we have to refer back to the actual mean. And this is simply telling us that for men who had no soy meals each week for an entire year, if we resampled from the same population, we can be 95% confident that the average sperm count will be between 2.61 and 7.36 or 7.37, right? And we can interpret the 95% confidence interval just the same for those who had 1 soy meal per week. So if we resampled from the population, we would be 95% confident that the sperm count for men who had 1 soy meal would be between 2.42 and 6.79. Right. And a little hint about the t-test. If these two bounds cross each other, then we're probably going to have a non-significant result, right? Because think again about what the t-test is actually telling us. The t-test is comparing two means and telling us if they are significantly different from each other. And already we can see that our estimated population means are well within the bounds of each other. There's quite a bit of overlap here. So it's probably the case that there isn't much of a difference in the actual population. But we can't confirm that without looking at the t statistic and the associated p-value. All right, so let's go ahead and try to interpret this bottom half of the output here. Now, remember when I said that the direction of the research question is really important? This is where that's going to come into play. Now, we technically have three separate p-values here, and the direction of our alternative hypothesis will define which one to interpret. Right? So these three here are different p-values based on the hypothesis. So let's write out our null and alternative hypothesis here. Now, the null hypothesis is going to be the same regardless of what the research question is. It simply is that mean for mean for 0 soy will equal mean for 1 soy, right? There's no mean difference. When our alternative hypothesis has a direction, we have to be really specific in how we write out the alternative hypothesis. And in this case, our alternative hypothesis is that the mean for 0 soy is greater than the mean for 1 soy. Okay, and this will help us identify which of the three p-values we'll be interpreting. And to do that, we have to understand what this difference value is here. What are we representing by that difference? While it might seem like there's a lot of confusing output here, stat is actually telling us exactly what it's doing, right? So it's calculating the mean difference by subtracting mean for no soy minus mean for 1 soy. Okay, so it's subtracting this mean here, 4.99 minus 4.61. Okay, and then we get a mean difference in this row of 0.38. So our actual mean difference here is 0.38. And we need to decide if that's a significant difference based on our null and alternative hypotheses. So let's take a look at each of these three p-values here. The alternative hypothesis for this p-value is that the difference will be less than zero. For the mean difference to be less than zero, that would mean that the mean value for no soy is less than the mean value for one soy. Okay, simple math here. If we subtract a larger number from a smaller number, we'll have a negative value. So the alternative hypothesis all the way on the left is that mean for no soy will be less than mean for one soy. So we know that this directional hypothesis is not telling us what we're actually asking. Okay, because remember, alternative hypothesis here is that mean for zero soy is greater than mean for one soy. The alternative hypothesis for the middle p-value simply states that the means are different from each other. So this would be an example of a non-directional hypothesis. In fact, you're probably mostly going to be interpreting the middle p-value in this unit. Again, it's really defined by whether you have direction or not. And when you have a non-directional hypothesis, you'll be interpreting this p-value, the one in the middle. However, we know that's not the case here. So this is not telling us what we're actually asking. And this leaves the p-value all the way on the right. And we can see that the alternative hypothesis here is that the mean difference will be greater than zero. Remember, the mean difference is simply no soy minus one soy. This would mean that no soy would have a higher sperm count compared to one soy. So we know that this is the p-value that we'll be interpreting for this research question. Now, if you think back to 105, a directional and a non-directional hypothesis are the same thing as a one-tailed or a two-tailed significance test. Now, something to keep in mind, whether you have a directional or a non-directional hypothesis, your t-statistic is always going to be the same. So in this case, our t is 0.247. So the hypothesis will really define what the critical t-value is. So our t-statistic of 0.247 is the same regardless whether we're interpreting this p-value, the middle p-value, or the one on the right, but the critical t will be slightly different. Now, Stata is doing all of this behind the scenes for you. You don't have to worry about what the critical t-statistic is. But one thing you might notice is that while the t-statistic is the same, our p-value or significance level is slightly different for each of these hypotheses. And again, that's because Stata is comparing against a different critical t based on the direction of our hypothesis. Now, at the end of the day, whether we had a directional or a non-directional hypothesis, it's pretty clear that the mean difference is not significant. But what we can see is that our non-directional hypothesis is the furthest away from significance compared to the other two. And our directional hypothesis is closest. So the non-directional p-value here is 0.81, and the directional hypothesis is 0.40. So when running these types of analyses, you really do benefit from having your hypothesis be directional and based on theory. But in this case, either way, our p-value is non-significant. So this states that there is no significant difference in sperm count for those who ate no soy meals compared to one soy meal. Remember, this is per week for an entire year. So let's take a look at research question 2. Now, for this one, we don't have a directional hypothesis. We don't have any preconceived assumptions about whether males who had 0 soy meals will be significantly greater than or less than those who had 4 soy meals. Right? We just want to see if they are significantly different from each other. Right? The command here is exactly the same. T-test no soy equals 4 soy. And again, this is unpaired. And we get just about the exact same output. Of course, we have the mean for no soy isn't going to change, and the mean for 4 soy meals. Remember, this is mean sperm count as a function of how many soy meals were eaten. Our mean difference for this comparison is 0.877, and based on a t of 0.58 and a non-directional hypothesis, the p-value is non-significant. So again, we have a non-significant difference. All right, so let's just quickly write out what the null and alternative hypotheses are for this research question. Now, our null hypothesis is going to be just the same as the last research question. No soy equals 4 soy, right? But this time, our alternative hypothesis is a little different. This time, we're just saying that no soy is different from 4 soy. Again, there's no direction to this hypothesis. We just want to know if they are significantly different from each other. And based on our p statistic of 0.56, remember we want to interpret this middle p-value here, we would fail to reject the null hypothesis and conclude that in the population, there is no significant difference in sperm count as a function of no soy meals eaten per week compared to 4 soy meals eaten per week. All right, and since this is revision, I'm going to go ahead and go through the last research question fairly quickly. I really just wanted to demonstrate how to interpret the output and compare these results to the one-way ANOVA. So our final research question asks if there's a significant difference in sperm count for men who had 0 soy meals per week compared to those who had 7 soy meals per week. Again, this will be non-directional. Right, this time we're comparing a mean of 4.99 for no soy to 1.65 for 7 soy. And the mean difference here is 3.33. Right, and here we have a t-statistic of 2.865. And remember, we're interpreting this middle p-value. And our p-value here is 0.0068. Right, so let's one more time write out the null and alternative hypotheses. No soy equals 7 soy. And the alternative is that no soy is different from 7 soy. Now with a p less than 0.05 in this case, we would reject the null hypothesis and confirm in the population there is a significant difference in sperm count as a function of number of soy meals eaten per week. Now, there are a few things that I want to bring up before we move on to the one-way ANOVA. And the first being that we haven't tested any of our assumptions. Now, assumptions of t-test are very similar to assumptions of ANOVA. And one of those is that we have equal variability across all levels of our independent variable. That simply means that our standard deviation for no soy should equal the standard deviation for 7 soy. And we can see that there is a bit of difference in the variability here. So it might be that we're violating an assumption of both t-test and ANOVA. That's something we're going to look at in part 2 of the practical. Now, the next thing I want to talk about is more related to the overall design of the study. Now, recall in the study, we have 4 separate groups of cisgender males, and we've recorded their sperm count after eating 0 soy meals per week for an entire year, or eating 1 soy meal per week, 4 soy meals, or 7 soy meals per week for an entire year. And what we've done here is run 3 separate t-tests comparing the group who had no soy to each other group in this data set. This means for each separate t-test, we're using the same no soy group, which means for each t-test, we're not comparing completely unique groups. In other words, the variability for no soy is the same for each 3 t-tests. And by running 3 separate t-tests, and not accounting for the fact that it's the same exact group, we're actually inflating type 1 error. This simply means that we're increasing the chance of seeing a significant difference where one might not actually exist. Now, the more hypothesis tests that you run, the greater likelihood that you're going to have a significant difference. But that's incredibly inflated when you have the same group that you're comparing across many different t-tests. Now, this was a really rigorous study. The researchers would have to confirm that in the no soy group, each participant did not have a single soy meal for 365 days, which would be really hard to manage. So let's say a few of our participants either didn't know that a meal that they were eating had soy in it or knew and didn't care. Now, if that's the case, we have that error in the no soy group, and we're comparing that to each of the other levels 3 different times, which would be highly problematic. So when you're doing your own work, you'd actually want to skip this step. You wouldn't want to do 3 separate t-tests using the same comparison group. You would want to do a one-way ANOVA. So let's talk about the differences here before we get into interpreting the output in data.